Ladies and gentlemen, it is my pleasure to present the talk on interval-based verification techniques for the analysis of uncertain fractional order system models. During this presentation, I'll firstly start with an exponential enclosure technique that can be applied to the case of ordinary differential equations. Afterwards, this approach will be generalized towards using a Mittag-Leffler type state enclosure approach for the case of fractional order differential equations. After the theoretical contributions, I'll consider a few illustrating examples as well as conclusions and an outlook on future work. Now, let's start with initial value problems with uncertainty in the initial states. For the case of integer order differential equations, we describe the right-hand sides of the differential equations by smooth function expressions that depend non-linearly on the state vector x. The uncertainty in the initial conditions is given by so-called interval variables, where the lower interval bounds are strictly less or equal than the corresponding upper bounds. Lower bounds are denoted throughout this talk by the underline, upper interval bounds by the overline parameters. Now, let's have a look at the uncertainty that may also arise not only in initial states but also in parameters. Those uncertainties can be included in the right-hand side of the differential equations by appending these integrated disturbance models where the uncertainty is shifted in the corresponding initial conditions. Nonlinearities that arise in control laws can be accounted for by substituting the corresponding functional expressions into the open loop dynamics. Now, what we want to do during this presentation is we want to avoid time-consuming gridding and Monte Carlo simulations, and these time-consuming simulations even do not allow for quantifying exactly the sets of reachable states at a given future point of time. In addition, we want to preserve asymptotic stability by representing non-diverging bounds for sets of state equations for which stability can be proven beforehand. This strongly related to the wrapping effect, and the wrapping effect is something that arises typically also in other simulation approaches, for example in Taylor series-based techniques such as V-Node LP by Nednady-Alkov. And with the help of the exponential state enclosures, we want to minimize the influence of such wrapping. Now, let's have a look at the definition of exponential state enclosures. There we have uncertainty, as already mentioned, in the initial conditions here on the right-hand side, and the state enclosures are defined by these exponential functions where the parameter matrix lambda is a diagonal matrix with interval entries on its diagonal. This allows us to evaluate the corresponding matrix exponential quite easily in symbolic form. Now, plugging in this definition of the verified state enclosure in the right-hand side of this PK iteration, where kappa plus 1 represents the outcome of the iteration, and the step kappa is the corresponding previously defined state enclosure, we can differentiate this expression explicitly with respect to time, evaluate it over some given time horizon, and substitute the corresponding right-hand side here by the functional expression of our set of ordinary differential equations. What you can see here on the left-hand side is that we have a multiplicative coupling of the yet unknown parameter interval lambda and an exponential term depending also on this unknown expression. Now, let's assume that the iteration procedure converges. If the iteration procedure converges, not only the parameters are mapped from one iteration step to the next into the interior of itself, the same holds also for the corresponding matrices, and further on also for the corresponding state enclosures, depending on the exponential functions. In such a way, we can over-approximate the term on the left-hand side that depends on the matrix exponential and divide through this term under the prerequisite that the value 0 does not belong to the set of reachable states. In such a way, we are able to formulate a verified state enclosure at the final point of time capital T. Now, this iteration procedure simplifies further for the case of linear system models. In linear system models, we can see here on the right-hand on the slide that the evaluation becomes fully overestimation free in cases that these parameters aij become equal to 0 except for the diagonal entries aii. This already tells us that we should transform the sets of state equations into a more or less decoupled form that corresponds to the Jordan canonical representation of the corresponding sets of state equations under the assumption of pairwise different eigenvalues. In addition, for the case of nonlinear systems, what we should use there is the corresponding floating point evaluation of the eigenvector matrix at some representative state and compute its inverse with the help of a verified interval arithmetic approach. Now, let's move on to the case of fractional order system models. And fractional order system models, here on the left-hand side, the differentiation order nu is a general, non-negative, real-valued parameter and not strictly equal to 1. On the right-hand side, we assume that we have either a nonlinear representation that is given by the function f, or factored out the state vector x in terms of this quasi-linear representation where a of x depends on state-dependent system matrix. Initial conditions for the differential equations of computer type are again specified at the point of time t equal to 0. In the case that this differential equation is linear, we can explicitly formulate the corresponding solutions by means of a Mittag-Leffler function. This explicit solution is given on the slide, where the two-parameter Mittag-Leffler function can be specified by an infinite series representation. In cases in which the differentiation order nu becomes equal to 1, the Mittag-Leffler functions becomes exactly equal to the classical exponential function. Please have in mind additionally that fractional order system models are characterized by an infinite amount of previous memory. That means if we want to stop the integration at some point of time tk plus 1 and want to restart then again, we have to account for the corresponding uncertainty that arises due to the temporal truncation. Now, a verified state enclosure for the fractional differential case can be defined as a generalization of the exponential enclosure that we had seen in the first half of this talk. We just have to replace the exponential function by the corresponding Mittag-Leffler term, where lambda is again a diagonal matrix with interval entries. Now, the following steps are again based on a PK iteration. We plug in the corresponding Mittag-Leffler representation of the state enclosure, over-approximate this term here in the iteration step kappa plus 1 by the outcome of the previous iteration state, and resolve this corresponding expression here towards the parameters that are yet unknown. Please keep in mind that overestimation due to coupling of the state equations can be reduced, again, as in the case of the integer order system models, if we transform the sets of state equations as far as possible into a decoupled form with an equilibrium in the origin. Additionally, I want to point out here in this slide that a further simplification of this formula is not as easy as in the case of the integer order scenario. Now let's have a look at a graphical representation of the Mittag-Leffler function, evaluated for a complex valued argument set and some differential order nu equal to 0.8. On the left-hand side, you see the real part, on the right-hand side, the imaginary part of the evaluation of the Mittag-Leffler function. During our presentation, we want to restrict ourselves to a purely real value scenario. That means we just have a look at this line here, where the imaginary part turns equal to 0, and we want to exploit certain monotonicity properties of the Mittag-Leffler function in this case. First of all, a verified enclosure of the Mittag-Leffler function for an interval argument can be determined by a lower bound that depends on an exponential term and an upper bound that depends on this rational expression. However, these bounds are quite coarse. To reduce the pessimism, we can make use of a floating point evaluation of the Mittag-Leffler function according to a MATLAB implementation that has been published by Rauh. This MATLAB implementation is quite precise, with a tolerance bound of epsilon that is in the order of magnitude of 10 to the power of minus 15. Using this information and downward rounding of the infimum and upward rounding towards plus infinity of the supremum and plugging in this information about the tolerance bound, we can end up with a verified interval bound for the evaluation of the Mittag-Leffler function in the real-valued case. Further on, we can exploit monotonicity with respect to two parameters. One of them is monotonicity with respect to time, and the other one is monotonicity with respect to the parameter lambda, as long as the upper bound of this parameter is strictly less or equal than 0. However, as shown in the proceedings paper, we have to treat uncertainty in the parameter nu with care. There, it may occur that the change of monotonicity properties occurs with respect to the parameter itself. Now, if we want to restart the simulation at some point of time tk plus 1, we have to account for the infinite memory property of fractional order system models. This can be quantified with the help of this expression, where mu is the uncertainty that arises from restarting the simulation at some point of time. Finally, I would like to have a look at an illustrating example. This illustrating example shows a nonlinear dependency on the state variable x with a third power and uncertainty in some system parameter p. On the left-hand side of this slide, you see small uncertainty. On the right-hand side, large uncertainty in the initial states, in the parameter, as well as in the differentiation order. Now, we want to compare three different cases. The first case is a short-time simulation. The second one in red, a medium-term simulation, and a long-term simulation in blue. For all of these scenarios, we calculated constant interval bounds lambda. And you can see that including not only the transient behavior, but also system states that are close to the equilibrium leads to an increase in the interval width of lambda, and therefore also in the interval width of the simulated bounds. Now, what we have to make sure in future work is we want to take into account the tight information of short-term simulations, also in cases where we want to perform long-term simulations. This leads us to one of the scenarios for future work, where we have to fuse information about the temporal truncation errors with the simulations that you had seen on the following slide. Now, let's come to concluding remarks and an outlook on future work. What you have seen during this talk is a computational efficient verified state enclosure technique that can be applied on the one hand to the case of integer order ordinary differential equations, and also on the other hand for fractional order system models. In both cases, where we're able to handle uncertainty that are given by intervals for the initial conditions and the system parameters. Future work will deal with cases where we have complex valued eigenvalues for fractional order system models, and this will lead us to the use of complex valued interval arithmetic. Further on, refining error bounds for temporal truncation errors will be one of the tasks that have to be considered. In addition, applications will deal with real-time capable predictive control strategies, the use of the simulation technique for safety analysis of controllers, for set-value state estimation like interval observers, for verification of nonlinear controllers concerning compatibility with state constraints. Now, before I thank you for your attention, I want to refer to these 4 related publications where further techniques concerning the real and complex valued exponential enclosure technique, as well as the evaluation of Mittag-Leffler type state enclosures for fractional order system models have been published by me and my colleagues. Thanks a lot for your attention.